Okay, hello everyone, I'm Joe. I am here to talk to you about functional Ruby. So let's get started with it. Oh, I have this remote for slides. That is disconnected. That's the end of that. My most important job is being a daddy to that cute little girl. Her name's Lucy. I promise I won't show any more pictures of her, but she's adorable. And I am on Twitter, GitHub, LinkedIn, at JLeo3. Say hello on any of those media. I'm a friendly person. My second most important job is that I run this company called Def Method. It's a New York City-based agile software consultancy. We do have openings for remote engineers, PMs, designers. If you are great at what you do, then we're hiring. And I wrote the third edition of this book. I co-wrote the third edition of this book. It's called The Well-Grounded Rubyist. And at this point, you might be saying, actually, Joe, this guy, David A. Black, wrote The Well-Grounded Rubyist. You did not write The Well-Grounded Rubyist. You are both correct and incorrect. David wrote the first two editions of The Well-Grounded Rubyist and made it super popular and this incredible text. And then they came to him and said, hey, David, could you write another edition of this for a more recent edition of Ruby? And he said, no thanks, I'm finished. But I have this friend, Joe, that would love to do it. And I did. And one of the things that I focused on was the fact that the thought that there was a trend toward functional programming in Ruby. And I think that this was borne out when, if you heard today's talk by Mats, where he talked about a lot of functional programming language features from languages like Elixir and F#. So I wanted to extend the book, and I did by writing this chapter called Ruby and Functional Programming. And David thought that was a good idea. He said, yeah, go ahead and do it. And I published a book, and here we are as Rubyists and also friends, happily together. If I had a nerd card, the top of it would say, loves to read fiction. And so I have decided I would intersperse some fictional books in here for no reason other than I love it, and they might be tangentially related to the slide, but also if you're bored and you're in like one of these seats over here and you can't get out without annoying a bunch of people, at least if you're going to Google something, I'll give you something good to look up. OK, so let's talk about functional programming and purity. What I've found is in the functional programming world, there is a lot of discussion about pure versus unpure or impure functional programming languages. And I actually think that that is a limiting kind of discussion. So let me break that down. Ruby is a functional programming language. That I think can be generally agreed upon because it supports first-order functions. By that definition, a language like Lisp, or insert your own pretty obviously functional programming language here, F# Elixir, Scala, Clojure, they're all functional programming languages. So what about Java? Ever since Java 7, Java has also supported first-class functions with closures. So also, functional programming language. And here's one you're really going to hate. PHP, since its beginning, the language that every Rubyist loves to hate, since its inception has supported first-order functions. Unfortunately, there are some people out there that do some really terrible things with PHP and give it a really bad name, but it is a functional programming language. So what's the problem? The problem is you can't look at this list and say, well, there's a list of functional programming languages, because they're not pure, and they are not thought of as functional programming languages first. So what makes a pure functional programming language? A purely functional language guarantees referential transparency. That just means that if you call a function with the same arguments, you will get a result, and you will get the same result no matter how many times you call that function with the same arguments. 1 + 1 = 2, and 1 + 2 = 3. And no matter how many times you call that, and that's a valid Ruby function, no matter how many times you call it, you'll get the same result. That's referential transparency. Ruby does not guarantee it, and we already know this because everything with a bang operator will change the state and give you a side effect and will not be referentially transparent. But importantly, Ruby does support referential transparency. More on that in a minute. A purely functional programming language will guarantee immutability, and Ruby does not. And you might say, well, hang on a second. Doesn't it support immutability? It does have frozen. It does have freeze. I'm thinking frozen because, you know, I've got a 4-year-old. But it does have freeze. So you could freeze an object, and then you can't change it. So isn't that immutable? And also, you know, Ruby 3, maybe there'll be frozen strings. And after today's talk, maybe not. But someday there'll be frozen strings. So doesn't that support immutability? Actually, no. If you dig into the source code of Ruby, you'll see that to freeze a string in Ruby is actually just flipping a bit. And if you can, and what's more is that if you flip that bit in, if you use a certain library, you could flip that bit even at runtime. So if you've got something that you call frozen that you can change at runtime, you really don't have immutability. So it's really not supported. Okay, so Ruby, functional language, not purely functional language. But that is a really strict definition. So by that definition, your favorite functional programming languages are not purely functional programming languages. Lisp is not. Scala is not. Clojure is not. Elixir is not. So what does that leave? Haskell. Are there Haskell programmers in here today? Anybody that likes Haskell, messes around with Haskell? There they are. Those are the people that are going to come up to me after the talk and tell me about all the things I got wrong, because they know that they have written, that they write in a purely functional programming language. And that's great. But it just doesn't apply to the mass of programming languages out there. And what I would argue is that it really doesn't have to. Most of the time, side effects are good. Even immutability can be good in certain circumstances. Side effects are, of course, necessary to do interesting things, like insert things into a database or print things to a screen. And while there are purely functional ways of skirting this and making sure that there are no side effects, you don't have to adhere to this to adopt a functional programming philosophy and a functional programming approach to your programs in Ruby. So what do most people mean when they talk about functional programming? They talk about removing side effects, and then it gets a little bit dicey. People may talk about lazy evaluation. They may talk about generics. They may talk about tail call optimization. I think if you're not in this room, then you're in the other room where they're talking about pattern matching. That's another big one. They'll talk about streams. And to be honest with you, in my first few years as a developer, those kind of concepts were intimidating to me. And to my discredit, I did not face that well. I didn't just challenge myself to learn it. But luckily, eventually I got it, I think. And even more fortunately, I found that there is a way to start. There is a way to get started and to teach yourself in a friendly environment. And that happens to be by using the Ruby programming language. Because Ruby really does support functional programming, and it has been doing this for a while, and it's just going to support more and more functional programming paradigms. So my goal today is to present what can otherwise be thought of as really complex information in a simple, easy to understand format. I'm even going to do some live coding. I'm going to make a bunch of mistakes. You can all yell at me. And we'll try to dive into some tough concepts and leave you understanding that you can take these concepts and build on them in your own work. Okay, so let's start with the easiest stuff. We all already know what side effects are, right? We know that if I create a string called Joe and then I upcase it, then my string is unaltered. There's no side effect there. And then as soon as I put an exclamation mark at the end of it, I've altered str forever, and I've just created a side effect. And if this was done outside the scope of a function, then I have altered the state of my program, and now I've just screwed everything up. I don't have a functional program anymore. But the exclamation mark is there, so side effect-free Ruby should be easy, except it's not. even things that we use very commonly have side effects. The double chevron is a side effect. It alters my array irrevocably. And so there's no exclamation mark there, and so we have to be a little bit careful of what we're working on. Another example, I think, can be with exceptions. So if I have this key that's in a hash, and I try to fetch a key that does not exist in that hash, I'm going to get a key error. This isn't such a big deal, except that when an exception is raised, this is a side effect. And if it's not handled within the function, then I can't guarantee referential transparency. I can't guarantee the result. And so all of this is to say that you really have to understand the language features. You have to understand that something that you're calling may raise an exception. You have to understand the context of when and where you are calling these things so that you can keep a side effect-free landscape for your code. Okay, let me give you a relatively pedantic example. You can skip this one. Here on your left is some suboptimal code. Anybody want to tell me why? This is an easy one. You can just shout it out when you know. Yeah?
What if divide by zero exception is raised?
Divide by zero exception is raised. Yep, right. No exception handling.
Mutating student from inside the method.
Yeah, I'm mutating student from inside the method. So the reason that I'm bringing this up is because, one, it's a pretty easy example. You know, examples like this exist all over Active Record, or even in Active Record helpers if you're using Rails, where we're saying, OK, calculate a grade, and while you're at it, update the student with that grade. And we think that it's a straightforward example, but it actually is not. When we dig a little bit deeper, we see that this function is modifying state. And so it is not side effect free, and it certainly isn't referentially transparent. But the reason I'm bringing it up, and on the right we have our other example that is doing one thing, and that is referentially transparent. The reason I bring it up is because whether you come at this from an object-oriented point of view or a functional programming point of view, you still are going to pick the one on the right. The reason is the one on the left, if you're using object-oriented principles, violates the single responsibility principle. That function is doing two things. It should only be doing one. It's also lying to me because it's saying calculate grade, but it's also calculating the grade and updating the grade on the student. And I don't like things that lie to me. But if I'm looking at it from a functional programming point of view, I'm looking at it and saying, well, this thing has a side effect. And I come to the same conclusion. So often, you'll see that functional programming design theory and object-oriented design theory can come at something from two different angles, but achieve the same result. All right, let's go a step deeper. Let's talk about currying. Currying is one of these things that sounds complicated, but is actually not very complicated. Currying is breaking down one function with multiple arguments into multiple arguments, each with one function. Currying is breaking down one function with multiple arguments into multiple functions, each with one argument. Okay? So let's do an easy example. Let's work with add. Here I'm going to use a stabby lambda, and I'm going to, oh, I don't want that. I want some A and some B, and we'll add A and B together. And what do we get? We get a lambda back. This is our add function. And it does exactly what you think it would do. So you call it with a couple of integers, and you get what you would expect. You get 12 back. By the way, you can also use the syntax call, but it's not needed. It's superfluous and lame, so I'm not going to do it. But you can do whatever you want here. You know, it'll add strings, it'll add whatever. It's not all that exciting, but it is one function with two arguments. So if I want the curried version of this, curried add, I would need to create two functions, each with one argument. So let's do this. I almost always get this wrong, so if I do, you can point it out to me. No, I think that's good. Okay, so that is the difference. So by hand, I have curried the add function from one function with two arguments to two functions, each with one argument. When I call it, it's slightly different. I can't just call it with the two arguments because the first function only takes one argument. So what I have to do is partially apply this function. I take the first argument, pass it into the function, and then I take my second argument and pass it into the resulting function. So two dot calls in there, and then it does what I expect. So again, the add function is, the curried add function is simply two functions, each with one argument. And what I did there, when I called curried add, was partial function application. So partial function application goes hand in hand with currying, and it's best to understand them together. Partial function application is when I pass in any number of arguments less than that function's arity. So the result is a new function with all of the functions, with all of the arguments that I passed in applied. In this case, we really only have two arguments with curried add. So if I pass in only one, what I get back is yet another function. And this is what I expect. When I call it again later with any other argument, sorry, let's do this. I call that again later with any other argument, and now the expression can complete and I get an integer back. This is just to illustrate. This is not valid syntax, but the add function here is being partially applied. So it's saying, okay, let's say I create this generic function. We'll talk about generics in just a second. Some point later in my execution, I get some new information. I learn the value of A. Well, I can pass in the value of A and simplify my function. What comes back is still a function waiting for that value of B. But I have partially applied it. Now, I've spent about 7 or 8 minutes talking about currying and partial function application. So if you don't get it after 7 minutes, that's OK. In fact, you don't really have to do it, get it all at once. And you don't have to do it by hand. We can take a lesson from Ignatius C. Reilly, the laziest of all fictional characters, and we can just let Ruby do it. So Ruby has a keyword called curry, and curry will manage both currying and partial function application. All you have to do is call curry, because it's Ruby. So you already have seen the add function. Now my curried add function is going to simply be add.curry. And the great thing is, when I call my curried add function, I can call it the way I think I'm supposed to, with partial function application, or I can call it with all of those arguments at once, and it will still work. It will not throw an argument error. So Ruby is taking care of this under the hood for me to manage both partial function application and currying. So it's pretty cool stuff. All right, let's do something a little bit more advanced. Let's find some multiples. And the reason I want to find multiples is because I want to start talking about generics. So finding multiples is another stabby lambda. It will take some x and some array, and it will search for x within that array, search for multiples of x within that array. So the array will yield an element. The element modulo x needs to equal 0. If it does, then I am done. And this does what I would expect it to do, namely it says, find me multiples of 3 in an array of 30, 40, and 50, or 650, because that's what my fingers did. And we get 30. OK, great. So I'm calling find multiples a generic, meaning it's nice, but it's not really solving a specific problem just yet. So before I dig into currying and partial function application with this function, I want to talk about generics and their purpose. In my opinion, generics are to functional programming what objects are to object-oriented programming, in that we want to create a generic function so that we can create individuated functions on top of that. So we use these generic functions as building blocks to build other functions. So we're trying to solve these problems rather than creating an object design around them. We are trying to create functions that can solve problems and then create individuated functions that solve those specific problems that we have at hand. Okay, so for a super simple example, we can create a function called find multiples of, and this is going to be my curried version of find multiples. Now, think about this in terms of objects and with either inheritance or with modularization. We could say, okay, I want to find multiples of 3. So that is simply partially applying this function with 3. Then when I want to use this, it will merely just take an array. Right? If I want to find multiples of 5, I can do the same. Right? Same data set, different result, because I have created some individuated functions off of my generic find multiples of function. So again, I'm taking these functions, I'm using curry, and then I am able to start using generics as building blocks for my higher order functions. Okay, let's talk about streams. So the reason I would want to create a higher order function, the reason that I want to create a generic function, is because I want it to operate against a large data set. So this is another difference in thinking between object-oriented programming and functional programming, where in object-oriented programming, you may want to solve a problem for some finite set of data. In object-oriented programming, in functional programming, you really want to create generic functions that will work for any set of data, for an infinite set of data, for example. So every integer from 1 to infinity, right? Or every word in the English dictionary. Now, every word in the English dictionary is a finite set, but it is very, very large. And you certainly can't calculate it if you're using a bunch of if-then statements. What you need is lazy evaluation, in which you say, okay, I want to take this stream of data and operate against only the data that I need, and then yield the results. So an example of this, we can find first multiples. So to find first multiples, we're again going to use our stabby lambda. We're going to use the multiple, and we're going to use the number, the first multiples that we want to find. From there, what do we do? What I'm going to do first, actually, is I'm going to use an infinite range. So as of Ruby 2.6, this is valid syntax. This just means 1 to infinity. You used to have to use something called float infinity or something like this, and it was, or this. Yeah, thanks. And this was annoying to write. So now we can do things like 1 dot dot, and that is our range from 1 to infinity. Okay, back to find first multiples. So what I'm going to do is I'm going to say, I want to find the first multiples, but I don't want to define the set of data that I'm operating against like I did the last time. When I was finding multiples the last time, you gave it an array, right? You had to provide an array. This time I'm saying, I don't want to provide any data. I just want this to work on all positive integers. In order to do that, I create that range, and then I call lazy so that Ruby knows, hey, don't actually operate against every integer in the universe until my computer explodes. Just operate on the ones that I need. After that, it works a lot like the last one did. I'm still going to yield an element. I'm still going to modulo that element against the multiple. I'm still going to test it and make sure that it equals 0. But then importantly at the end, if that fits on the screen, I'm going to call first and I'm going to pass in the num variable. So now I can say, give me the first 10 multiples of 100 or whatever. And it should just do what I've asked it to do. So find first multiples. Sorry, let me put this up here. Find first multiples. And I say, OK, the first 10 multiples of 100. And that does what I expect it to do, I think. Or find first multiples, first 3 multiples of 12. Nope, thank you, no dots. Oh, I got that backwards. First 12 multiples of 3. I think I had this differently in here, which could only be confusing. So passing in the number and then the multiple, finding the first multiples would say, OK, find the first 12 multiples of 3, find the first 100 multiples of 10, and on and on. The important part, I think, here is that with my lazy selector here, oops. With my lazy selector, I'm now able to create a generic function that is going to operate against any set of positive data. OK. We've got a little bit of time left, about 13 minutes, so let's teach you recursion. No, I'm just kidding. I am not going to attempt to teach recursion during this talk. There are far better teachers of it than me, and probably you know it if you're sitting here already. But I am going to talk about the terminal clause. And the terminal clause in any recursive function is the thing that stops you from recursing. So that clause that you hit, that when you test against it, you say, OK, I'm done, now return the result, that's called the terminal clause. The terminal clause is important when you are writing recursive code if that recursive code is set to be tail call optimized. And so now we're getting really deep into the, excuse me. So now we're getting really deep into some of the functional programming paradigms. But I'm going to argue that it's still not all that complicated. In order to implement tail call optimization, you need to do two things. The language needs to support it, and you, the developer, need to write code that can take advantage of it. And it may surprise you to know this, but Ruby is a tail call optimized language. However, you have to tell it to optimize your tail call recursive functions, and then you have to write tail call recursive functions. OK, some popular recursive functions you'll see here. We're going to take factorial and write it in a recursive manner, and then a tail call recursive manner. So in order to get Ruby, at least MRI Ruby, to optimize your functions, optimize your tail call recursive functions, you need to tell it up front to optimize itself. So you do it with these couple of lines, instruction sequence that we give to the compiler or to the interpreter to tell it to optimize itself. I kind of like that it just says tail call optimization true. I would like it even better if this were not something that I had to require, but, and that it just came standard. But I'm sure that will come soon in Ruby. So I'm not going to type this out. Luckily, I don't have to. I have a file here that has it in there. And so I'm going to require it. Once I do, I can write tail call recursive code, and it will optimize. So let's do this with an example. Here's factorial. And this is a totally valid way to write a factorial recursive function, I hope. So we can return x if x is equal to 2. And if not, we can call it and multiply it by x. And this should do what I expect. I think it does. Yeah, that won't work. So what does it have to be there? X less than or equal to 1? could be less than or equal to 2. There we go. So this is a valid way of writing factorial. However, it is not it is not tail call optimized. So I can call, no, that's not right. No, that is right. So I can call factorial, and I can call it on a number of different things, but I can't call it on something too large, or I get a system stack error. So how can that be? I already told it to optimize itself. Well, the reason is because this function is recursive, but it's not tail call recursive. Okay, so a tail call recursive function is one in which the last line is a call to the function itself. So one more time. A tail call recursive function is one in which the last line is a call to the function itself, and only a call to the function itself. So in this example, you could see that I am calling the function. I am recursing and calling the function, but I'm multiplying the return value by x, and that's not tail call optimized. In order to have a tail call optimized function, I have to only call factorial. So to do that, what most functional programmers do is they use an accumulator. An accumulator accumulates things. So we'll use x, and we'll use accumulator equals 1, and we'll do this just a little bit differently. We'll say return accumulator if x is less than or equal to 1, and if not, we have to just call factorial, and then the arguments become important. So we have factorial, we'll give it x minus 1, and we'll also give it accumulator times x. Now, when I first looked at this, I thought it was cheating. It's not, because in this example, I am only calling factorial, and I'm not doing anything else to it. And what I do within those arguments is less important to the Ruby interpreter. It will optimize this. So if I've done this right, then factorial of 4 does what I expect, and factorial of 24 does what I expect, and factorial of 24,000 will work. And that is the correct number, I know. So this is the comparison left to right. An accumulator is something that is often used, especially in recursive functions, and especially with tail call recursive functions, because it allows the interpreter to optimize. It can allow you to do larger calculations, as you've just seen. It should also optimize, meaning make even the smaller functions or the smaller data sets resolve much faster. So the computation should happen much faster, regardless of whether it's going to trigger a Stack Overflow error or not. Okay, so where can you learn more about this? Well, there's one way. You could get the book. Manning has a 40% off for like every Manning book that's going on right now. And I tweeted the code, but I also have it somewhere, so you can see me after this and I'll give it to you. Also, I was really thrilled to work with Abdi Grimm and the Ruby Tapas team to create a Ruby Tapas episode on partial function application. And in that episode, I dive deeper into Curry to show you a couple of other things that Curry can do. It's really pretty interesting. And that's all I have. Thank you, everybody, for coming and for listening.